to my home chapter, so I'm really happy to kickstart this term of distinguished lecture in this way. So, designing zero carbon buildings, embodied and operational emissions in achieving true zero. Why do we need zero carbon buildings? Carbon dioxide reduces optical transparency of atmosphere, and buildings contribute quite a lot to carbon emissions worldwide, around 40%. And there are significant risks to biosphere and to all of us if we have an increase in global temperatures by 1.5 degrees after the pre-industrial level. So we are en route to reaching 1.5 degrees by 2034, and we can still generate 900 gigatons of CO2 and stay within temperature increase up to 1.5 degrees with 17% probability. This is referred to as carbon budget. Can we achieve emissions reductions? Well, if we look at how many minutes of solar radiation takes to provide enough energy to run the world for 1 year, in 2021, it took about 42 minutes, and in 2050, it will take about 53 minutes. This talk will be around 50 minutes long. So during this talk, the solar radiation intercepted by the Earth will be enough to run the world for a year. It is just we don't have the technology to utilize all this energy, and we need to focus really strongly in that direction. Now, the way we design zero carbon buildings is that we start from site and climate consideration, then we design geometry, design insulation, consider solar gain, solar shading, thermal mass, ventilation, lighting, and all of that goes towards heat balance and achieving thermal comfort. In fact, designing zero carbon buildings without achieving thermal comfort doesn't make sense. We need to achieve thermal comfort for building users and then make the buildings zero carbon. So if we put operational emissions on one side of the scale, represented conceptually in this way, and we put renewable energy on the other side of the scale, then operational emissions are balanced with renewable energy and zero emissions are achieved, aren't they? So we can all go home and this talk would have been very, very short. Except there's an elephant in the room. There's embodied carbon emissions that we need to consider, and renewable energy used to balance operational emissions can't balance embodied emissions anymore. So we need to make the elephant smaller, so to speak, and put more renewable energy on the other side of the scale in order to achieve true zero. And this can be achieved using less carbon-intensive materials and more renewables to achieve true zero. Otherwise, we can overshoot by 3 to 4 decades achieving zero carbon. How do we know this? Well, my colleagues and I conducted research into affordable housing development in the UK, and that housing development complied with building regulations, but the new houses were not designed to achieve zero emissions. We conducted simulation analysis on these houses, and you can see on the vertical axis we have carbon emissions in kilograms of CO2 per square meter of floor area, and the starting point here are embodied emissions. And houses as designed and approved for planning were going to produce operational emissions that were going to be rising all the time. There would be no chance of achieving zero emissions with that design. If those houses were to be retrofitted in 10 years' time, as they will have to be. In fact, we are building houses now which will have to be retrofitted in very near future, which is kind of beyond belief. But if we retrofit those houses in 10 years' time, then there's this kink of carbon emissions due to embodied emissions attributed to retrofit, then with renewable energy, those emissions are going to be falling down, but there's no chance of reaching zero carbon by the end of the century. If these houses were designed with conventional materials and with renewable energy, then emissions would be falling down slowly, and by 2065 we would reach zero. But if we used hemp-lime biocomposite or other biosourced materials, so that embodied emissions, the starting point is much lower, and apply the same amount of renewable energy, then we would reach these the zero emissions by 2045. So that inspired me to develop a zero equation to answer the question, when is a building going to achieve zero emissions? And the first term of the equation are embodied emissions in materials. The second term, positive operational emissions from non-renewable energy that occur from year one. And the third term are negative operational emissions arising from renewable energy that occurred from year one. And T is time in years when zero emissions are going to be reached. So these two quantities on the left and right need to be in balance in order to achieve zero emissions. And after solving the previous equation for T, we can answer the question, when is a building going to achieve zero emissions? So with only three numbers shown here, we can determine the building emission status in future years. Now, there's an analogous representation of the zero equation, and that starts with a representation of the building as a jam jar. Jam in the jar represents combined embodied and operational emissions. And then we have a small spoon that feeds jam into the jar that represents positive operational emissions arising from using fossil fuels. And then there is a larger spoon that represents renewable energy that removes the jam from the jar. The question is then, when is the jar going to get empty? When will the combined embodied and operational emissions going to get down to zero? What we need to do is take both spoons and at the same time put, with the left spoon, put jam in and take a bit more jam out. And depending on how many times we do that simultaneously, that'll be the time when that'll be the number of years that will elapse until we reach zero. So this is conceptual representation of the zero equation. Now, what if the building has a renewable energy system, but that system is not enough to achieve zero emissions by a specified year? We can modify the zero equation by breaking up the embodied emissions into constant embodied emissions in materials, and also base level of variable emissions arising from changing the size of the renewable energy system. And then, as before, positive operational emissions remain unchanged. And then on the right-hand side, we have base level of negative operational emissions arising from renewable energy system that occur from year one. And as before, T is time in years, and F is base level multiplying factor. So by solving this equation for F, we can answer the question, how much to increase renewable energy system to achieve zero emissions in T years. Okay, and jam jar representation of this is that we increase increase the embodied emissions in the jar by this much, and we increase negative operational emissions in the larger spoon by this much, and then that represents factor F, this increase here and that increase there. So designing a zero carbon building will be explained in 3 steps. Designing for negative operational emissions, designing for reduced embodied emissions, and application of zero equation to achieve the zero target year. First, designing for negative operational emissions. We will run through this relatively quickly. First consideration is site and climate. And one of the first considerations is the wind direction and wind intensity. So this is called wind rows, this diagram here for direction and for intensity. And here's our building in the center. And with that information, we can do simulations of an unprotected building or protected building with shelter planting and see what happens. Also, sun path diagram is very important for site data. It tells us for a particular location where is when the sun is going to be at what angle, at what time of the day, what time of the year. And if we draw a line through the center of this sun path diagram, which represents the facade of the building, then we can tell that, for example, on 21st of June at around 8 o'clock, this facade will start being illuminated by the sun, and the sun angle will be 25 degrees. That's for Birmingham in the UK. We can change the direction, change the orientation of the building, and again get similar kind of information. And with that information, we can then run scenarios of testing the shading, testing the shelter planting for a particular day or a particular time of the year. Of course, we have weather data for the site location, and this comes in various forms, such as monthly total solar radiation on various orientations, or hourly solar radiation on a horizontal surface, or in fact various parameters, including temperature, relative humidity, wind velocity, direction, and so on. Geometry is a very important consideration for designing zero carbon buildings. And I would urge colleagues to design shallow plan buildings. These are buildings that have a maximum of 12 meters between opposite sides of the facade, opposite sides of facade with windows. Because with these kind of shallow plan buildings, we can achieve natural ventilation and natural daylight in the core of the building and throughout the building. If we have deep plan, which is larger than 12 meters deep, then we won't be able to achieve natural ventilation, natural daylight here. We will have to use conventional energy, which causes carbon emissions. We can, however, break that plan, that deep plan down with an atrium and achieve 2 shallow plans that correspond to the original deep plan, and that avoids the need for using as much of conventional energy for ventilation and daylight. Volume to surface ratio of buildings also matters. These 2 conceptual buildings have exactly the same volume, but this structure, which I call tall box, has much larger surface area than this structure, which I call compact box. And if you look at heating plant sensible load for a year in the tall box, this is much larger than in the compact box. So this is another consideration to save on carbon emissions by doing compact designs. Insulation. where to put insulation. This is a scale model experiment with nested boxes, and inside this box there's a tube with hot water and a temperature sensor linked to a data logger. And we have two scenarios: insulation inside with high density material outside. This outside material is sand to represent high density materials in bricks, such as in buildings such as bricks or concrete. And this is shredded newspaper representing insulation. And then reverse situation in the other box, where we have insulation outside and high density material inside. And when we do the monitoring of this, we insert the hot water tube there. We can see that with insulation inside, we get rapid temperature rise and then the temperature falls. But insulation outside, we have slower temperature rise and slower temperature fall. Solar gain. There are several solar gain systems. There's direct gain system with large south-facing glazing and high-density material on the floor and the back wall. And solar radiation hits the floor and is re-radiated several hours later into the space. Trombe wall, again with high glazing on the south-facing side, and high-density material of which this wall is made, and heat is absorbed in the wall and reaches the inside. It's radiated to the inside many hours later. And we also have openings at the base and top to circulate air through the cavity by natural ventilation. Okay, isolated gain is a sun space with high density flow. Solar radiation is absorbed there, and heat is radiated into the space, and then there's openings at the top and base to exchange heat with the sun space and the internal space. Trombe wall has this kind of characteristics of time lag and decrement factor. So on the outside surface of Trombe wall, we get maximum temperature around sometime in the afternoon, and the inside on the inside we have maximum temperature many hours later. Time lag for about 300 millimeters wall would be around 12 hours. But many people here would remember attending a BIPSA conference in Rome about, when was it, in 2019, where the auditorium was inside an ancient building that was built in well, I think it was 700 AD or something like that, and walls were about 1.5 meters thick there. So that time lag and decrement factor, I can just imagine what they were, but you couldn't feel much inside on a very hot day in Rome outside. Okay, I have conducted scale model experiment of Trombe wall and direct gain systems. In both cases, the high density material is sand, and this is on my windowsill at home. And in the back of these boxes, there are temperature sensors connected to a data logger. And in the simulation of internal recording, monitoring of the internal temperature shows that there's much more rapid temperature rise and fall in the direct gain model, this one here, than in the Trombe wall model. So the red line rises slower and falls down slower. Shading is an important parameter for zero carbon design, and some path diagram will give us information about solar angles that we need to design solar shading. So this angle here angle alpha is obtained from the sun path diagram, and we want shading to protect the building from morning to the afternoon, from month A to month B. So with this information obtained from the sun path diagram, we can design the length of the overhang so that it covers, so it shades the window. And we can also design the louver blinds for that particular angle. But if we have tall glazing, then we can combine overhang and louver blinds to shade the entire height of the window. Otherwise, the overhang might need to be very, very long, which is not practical. And with this information in mind, then we can run simulation of a building that we are considering. And if we choose our position, our observer position, to be sitting on the sun conceptually, then whenever we see the glazing from that sitting on the sun position running through different hours of the day, then this is where shading is not protecting the building. So this is shown for Portsmouth on 21st of April from 7 a.m. to 6 p.m. Thermal mass is a very important parameter for zero carbon design. To understand thermal mass, we first define thermal capacitance, and that is mass times specific heat. And we also need to understand what time constant is, and that is the time required for an observed system parameter to reach 63% of the change between its initial and final value after the system receives a step input that causes that change. So we can now define thermal mass as encapsulated in the relationship for the building time constant. Building time constant is capacitance divided by the overall UA value. And if we sum up the capacitances and UA values for all surfaces, all materials, then we get the overall time constants of the building. And thermal mass is a relationship between the building thermal capacitance and the overall transmittance area product UA of the building, which through the time constant Tc gives information on the speed of response of a building to a heat input. We have two different scenarios here. Without nighttime ventilation and with nighttime ventilation. And we have a conceptual example of low thermal mass represented by the blue line, and high thermal mass represented by the red line. And the green line is a trigger point for air conditioning. So if we have several sunny days, and thermal mass is charged in the building but not discharged with nighttime ventilation, then there will be accumulation of heat. And with a low thermal mass, that accumulation of heat will be reaching the trigger point for air conditioning, for running air conditioning. It would reach that trigger point much lower with high thermal mass. But if we run nighttime ventilation and manage to discharge thermal mass sufficiently, then it could be that we don't even need to air condition the building when we have high thermal mass, because the trigger point for starting air conditioning will never be reached. But if we have low thermal mass, then that trigger point might be reached every day, and we might be spending more energy and producing more carbon emissions. Again, the scale model experiment, there's thermal insulation in the cavity, or sand in the cavity, representing high thermal mass here and low thermal mass here. Well, the tube with very hot water and temperature sensor going into a data logger. And we can see that in the case of insulation wall, this is low thermal mass, temperature rises fast and then goes a little bit faster down than in the other case, where in the high thermal mass insulation wall, external, the sand wall, temperature rises much slower, and then falls down much slower because we have absorbed heat here, which feeds back into the inner box. Ventilation is another very important design consideration. In addition to discharging thermal mass, we want to control the temperature of the building in different ways and different times. There are two mechanisms for the natural ventilation. There's wind effect, which is based on pressure difference between the windward side and leeward side, and that pressure difference drives the air through the building. Or we have stack effect, where we have a buoyancy of air and temperature difference between base and top of a tall space, and that buoyancy of air will drive the air circulation upwards if we create openings and open them at the base and top. And if we exaggerate this situation with high density wall in the back and a glazed surface here in the south, and perhaps an additional heavy high density material suspended from the ceiling, then intensity of stack effect will be stronger. I can demonstrate this with a scale model experiment of natural ventilation, where the experimental setup is the rainwater pipe, down pipe, which I've cut in the base to create an opening, cut it at the top, and glazed it with a transparent sheet. This has a lid on the top, and there's a saw blade that I will use as part of the experiment, and there's halogen lamp, a high energy halogen lamp, and I heat up the top of the pipe, which has a dark background, so it absorbs energy from the halogen lamp, and I place the smoke source not quite near the opening, a little bit away from the opening, and with the lid on the top, the smoke rises next to the pipe. But when I remove the lid, the smoke starts going into the pipe, and if I put the saw blade, metal saw blade there, and heat it up, then the angle of smoke going into the pipe is sharper. So this shows how natural ventilation works through stack effect. If we cannot manage to control temperature with natural ventilation, then we need to deploy mechanical ventilation with heat recovery that uses potentially fossil fuel energy and causes carbon emissions. But if we do that, we need to apply a cross-flow heat exchanger, which is very, very efficient, so that the incoming air and exhaust air cross each other but never mix. Lighting is another important consideration, and we first need to define the daylight factor, which is a ratio between average internal illuminance on the horizontal work plane and external illuminance on the horizontal surface, and that is multiplied by 100 to get values in percentages. And for daylight factors of 5 and above, the spaces that have daylight factors of 5 and above are predominantly daylit, but spaces with daylight factor of less than 2 require electric lighting. And this is a clear sky simulation of 3 different models: shallow plan model, deep plan model, and deep plan double height model. And in office spaces, we need around 300 lux for conducting desktop work. And here there's more than that in the back of the shallow plan building, but in the back of the deep plan building, there's far less than 300 lux. If we increase the height of the deep plan building, we double the height from 3 meters to 6 meters, then we've converted a deep plan into shallow plan effectively, and we have a decent amount of daylight in the back. We need to integrate daylight with electrical light, and this can be done by zoning. So we can have outer zone next to windows, and then inner zone that is away from windows. And then we also need to have occupancy switching, daylight switching. So when daylight increases, lights are switched off in the building. And we can also have daylight following, which means that lights are proportionally controlled, proportionally to the amount of daylight coming in, so that daylight and electrical light always provide equal amount of light in the building. So this all goes then into heat balance, and heat balance in a building is a complex phenomenon consisting of heat inputs and outputs, heat gains and losses, and that all results in a temperature balance in the building. And we, of course, want to achieve thermal comfort, because without thermal comfort a building, there's no point of designing zero-carbon buildings. Now, if we have metabolism, our inner energy source, in balance with heat transfer mechanisms from our body, then we are feeling comfortable. And if our metabolism is low and we have high heat transfer mechanisms, then we are feeling cold. But if we have high metabolism and low heat transfer mechanisms, then we are feeling hot. And Danish scientist Fanger experimented in the 70s with thermal comfort and devised a 7-point scale where thermally neutral point is 0 and -3 is cold, very cold, and +3 is hot. And then he derived a predicted mean vote, which is a vote by individuals about their satisfaction of thermal environment. And that predicted mean vote is an independent variable for predicted percentage of dissatisfied, or PPD. But you can see here that even with thermally neutral predicted mean vote, we get 5% of dissatisfied people. But in order to make the building perform satisfactorily for occupants, we shouldn't go more than 10% of PPD. And you can see that this is somewhere here. If we go further away from thermal neutrality in either direction, then predicted percentage of dissatisfied goes up exponentially, and people are going to be uncomfortable. So now design integration for negative operational emissions. Here is a conceptual solution landscape where every point in this landscape represents a design recipe for negative operational emissions. And if we look at God's view, here as I call it, and start serial search for the optimum solution from this point, then look what happens if we take pedestrian's view. The landscape looks the same in all directions, and we don't know where to go, and we are never going to find an optimal solution. We are very likely going to look in a local optimum, not in a global optimum. But if we take another God's view and spread our starting points across the landscape, so we are going to do multi-point parallel search, then we are much more likely to get to the optimum solution quickly. So multi-point parallel search is in fact multi-objective optimization. And objectives for zero carbon design, for operational zero carbon design, are to minimize carbon emissions, minimize cost, and maximize comfort. Now, we can't have more than two objectives for multi-objective optimization. So we will deal with the third objective by changing it into a constraint. So we will say that we want to achieve, we want to find these optimum points, a series of optimum points, which are called Pareto front, which are the closest to the origin of the coordinate system, but we don't want to allow comfort to slip beyond certain number of this comfort hours. So the workflow for designing negative operational emissions is to set the base model and then set design variables, set comfort constraints, set cost versus CO2 optimization, run optimization, and then have we found negative CO2 Pareto points? If yes, then we have achieved operational zero carbon emissions. If no, then we make changes and rerun. And I will show this on an example of an office building near Portsmouth, which has natural ventilation, high amount of south-facing glazing. Natural ventilation openings are shown in the base and the top here, and it has air to water source heat pump, where water part is distributed through underfloor heating system. And here we have chosen 9 different variables for design: air tightness, wall construction U value, roof construction U value, thermal mass for the ground floor, thermal mass for internal floors, glazing, external window opening, lighting power density, and using all 14 PV clusters. PV clusters are clusters from the overhang. I've divided them into 14 different surface areas. Okay, so with this, this is 9 variables. We get 3.3 million solution points, and this is therefore 9 dimensional problem, 3.3 million solution points. A solution landscape is much more complex than 3-dimensional, and there's no way with single search from a single point that we reach global optimum. We need to take multi-point parallel search using multi-objective optimization. And this is an example of a first optimization run. And there's a Pareto point with negative carbon emissions here. But I was a little bit bothered about this point here, which is even with lower carbon emissions, but it failed the comfort constraint. So I went and changed the variables slightly here, changed external window openings, and used 2 clusters of PV instead of 14. That brought down solution space to 472,000. And with that, I've then achieved negative Pareto point with negative carbon emissions of more than minus 500. So that gives us then the recipe for this design of the building. When we tap into this point, that gives us the recipe for design, and we use this recipe as one part of the solution, which deals with operational zero carbon design. Now we want to design for reduced embodied emissions, and embodied emissions in materials are calculated by using mass of the materials times emissions factors, which you can get from various databases. So when we multiply these 2 quantities, we get embodied emissions in the material. And this also happens to apply to air to water heat pump. I found emissions factor for that particular heat pump. underfloor heating system pipes. I had to measure the pipes, I had to disassemble them to see what is inside, and treat different materials differently, find different emission factors. I did that for manifold and valves, and then wiring, the same story again. For lighting and electric sockets, I measured the wiring and disassembled the wiring so that I have the copper, the insulation and so on. LED lamp fittings, the same. Electric sockets, the same, and ventilation system, the same. Now, there is a small but increasing number of products with Environmental Product Declaration, or EPD, which will give information about embodied emissions, and that will save you a lot of time. Embodied emissions from maintenance also had to be taken into account, and the service life is normally considered to be 60 years for buildings. And in this service life, I wanted to replace the heat pump every 20 years, solar PV once in 30 years, and LED bulbs every 10 years. So replacement frequency is 2 for air source heat pump, 1 for solar PV, and 5 for LED bulbs. And embodied emissions resulting from these replacements are shown here. Okay, so then embodied emissions from construction need to be looked at by looking at the phases of construction work. And in this particular example, there's 29 weeks duration of construction. First of all, preparation, foundations, floors, walls, and roof construction, installation of mechanical and electrical systems, interior finishes, and then connection of services, landscaping, and final exterior work, commissioning, and handover. And we then need to consider embodied emissions from travel of construction workers. So I'd like you to pay attention just to the headings on the table. Numbers are there just to illustrate what was calculated. But for construction phases here, 1 to 5, we need to see how many people are coming to the site. So they were coming by vans, how many vans they were using, how many days, miles traveled per day, miles traveled in total, kilometers traveled, because emissions factor is in grams of CO2 per kilometer, and then total emissions are calculated by multiplying all this. Embodied emissions from operation of site machines. We have construction phases for site machines, hours of operation, days of operation, power of site machines, emissions factor or grams of CO2 per kilowatt hour of the site of the site machine, and then total emissions are calculated by multiplication. Embodied emissions from material deliveries. We have construction phases, and then for each construction phase of assigned the percentage of materials delivered. We have around 208 tons of materials to be delivered, and this was to be delivered by 7.5 tons trucks, and then that enables us to calculate number of trucks required, miles traveled per day, if we assume that it's 30 miles turnaround distance, total miles traveled, total kilometers traveled, emissions factor again, and multiplication of all of this gives us the total emissions from material deliveries. And then we need to consider end-of-life emissions, deconstruction, demolition, transport, and disposal. Deconstruction and demolition are based on a gross internal flow area, and then there's an emissions factor for this, and then total emissions are calculated by multiplying the two. Transport emissions from deconstruction and demolition is similar to what we already explained for deliveries of materials, so it's the same kind of calculation here. And disposal emissions are based on mass and disposal emissions factor and total emissions. And then PV system also has embodied emissions. There's 90.92 square meters of PV that can fit on the roof overhang, and this is allocated to base level operation and embodied emissions from PV. And embodied emissions in the solar PV system is calculated in 3 scenarios. First scenario is for the current time with quite high values, and this is per kilowatt peak, so kilograms of CO2 per kilowatt peak. This is the embodied emissions factor. But in 20 years' time, there are literature sources which say that this is going to come down quite considerably. It's still kilograms of CO2 per kilowatt peak. So I've used this value as a starting point, and this value for maintenance emissions and total emissions from the PV starting point and maintenance in the first set of calculations shown here. But I also found an environmental product declaration for a particular PV system, and that was in kilograms of CO2 per square meter, and that is much lower, and I will use that as a third scenario. So application of the zero equation to achieve the zero target here. Zero equation plus high embodied emissions in PV in scenarios 1 and 2. We've calculated F factor defined previously, and now we substitute values into the equation for F factor, and for conventional materials. Is somebody speaking? So for conventional materials in scenarios 1 and 2, the F factor is 3.158, and if we use that for biosourced materials, then it's 2.244. And here is the diagram for unchanged solar PV as it can fit on the roof. We have starting emissions due to embodied emissions in materials and PV shown here, and going slowly down. The kinks here are due to maintenance emissions. But if we apply F factor to conventional materials and increase PV to this much, then we will achieve zero emissions, total zero emissions cumulative and operational by 2050. And if we use hempcrete wool and much smaller increase of PV, then we will achieve zero emissions there in 2050. You can see that in both conventional and hempcrete wool, starting emissions are higher than the starting emissions of the unchanged system with PV fitted on the roof. And this is because PV itself has embodied emissions, as we now know. Now, if we if we now go into scenario 3 and substitute the values of embodied and operational emissions for conventional materials, we get F factor 1.636, and for biosourced materials, it's 1.163. And now we have for unchanged PV on the roof, again, we're not going to ever reach zero emissions in this century, but in the case of conventional material, we are going to reach that by 2050 if we increase PV to 148, 49 square meters. And with hempcrete wool, we're going to reach it again in 2050 if we increase solar PV to 105.7 rather than 90.92 square meters. Okay, discussion. We are getting near the end. Having negative operational emissions is a necessary but not sufficient condition for achieving zero cumulative emissions. We must account for embodied emissions as part of zero carbon design. And to achieve zero cumulative emissions, operational and embodied, with certainty and by a specified year, the zero equation helps to establish the magnitude of negative operational emissions required. Increasing the size of PV system will reduce operational emissions, but it will increase embodied emissions from that system. Serial search of design landscape for optimum design may or may not find the best solution, and in fact it is very unlikely to find optimum solution. We are likely to lock into a local optimum. And parallel search of design landscape from multiple points using genetic algorithm can pinpoint the optimum design with more certainty. Multi-objective optimization facilitates the parallel search and should be used for design of negative operational emissions. And there are, of course, uncertainties in embodied emissions figures. And despite these uncertainties, this approach provides more certainty in comparison with not considering embodied emissions at all. And therefore, to conclude, to design zero carbon building with certainty and by a specified year, we need to design for negative operational emissions using multi-objective optimization, design for reduced embodied emissions using biosourced materials, and apply the zero equation to establish the amount of renewable energy required to achieve combined embodied and operational emissions by a specified year. You notice that I didn't give any reference sources for embodied emissions. There are quite many of them, and you can find this online. They're changing all the time, but they are there, and you can use them for your designs. So, my name is Ljubomir Jankovic, and thank you for listening.
Thank you very much, Professor Ljubomir. Very insightful, very relevant, and very interesting. So, yeah, thank you very much. So can I invite attendees if they have any questions, if you don't mind putting your hand up and I'll call your name out and ask questions. I just saw a hand go up a minute ago. No hands. Okay, so on the chat, there was a question about the model. One of the attendees was asking, are those stacks on the roof in the model or solar tubes? I'm not sure. Sorry, Paul, if you could.
No, those, okay, what a person, oh, I see, something about geometry. Could a colleague please come on the speaker and say the question, because I can't see the question.
Okay, yeah, like you were presenting, it looks like it was completed in design builder, the model, and you show the geometry. There were two stacks in the model, so I don't know if you are representing those are stacks only, or those are kind of solar tubes to take advantage of the lighting.
They're not solar tubes, they're stacks. They are just stacks.
Okay. And when you model that, what is the purpose? Because at the end you can increase infiltration, or is it more accurate to throw stacks in the model? Why would you do that?
I don't understand the question.
Yeah, like what is the purpose of modeling those stacks? Because normally, if you are going to have some infiltration or exfiltration throughout those elements, I don't know if it is recommended to just increase the infiltration, or is it more accurate?
What is the point? Okay, what is the point of modeling the stacks? The point was that the stacks were in the building. I just modeled the building as close to what the building geometry was as possible, because if you start simplifying, as modeling is already an approximation, and there's a degree of simplification in every model, and if you start oversimplifying, then the model is going to be less and less accurate. So that was why I modeled the stacks.
Okay, Thank you.
Okay.
Very detailed
Thank you very
analysis, by the way.
Okay.
Thank you very much, Paul. There's another question from Nicholas.
Okay. I wanted to ask about insulation. Does it last up to 60 years, or it will last maybe 15 to 20 years, and you have to do a refurbishment again? So it means that we add more embodied carbon, or you should choose insulation which lasts up to the end of the life of the building.
Oh, I see. Okay, so basically, do we replace insulation during the lifetime of the building or not? Yeah, that's a very good question. I haven't thought about that. Insulation can be replaced in some buildings much more easily than in other buildings. For example, in a building retrofit that I was involved in, thermal insulation was injected into the cavity, and injection of insulation was combined with injection of an adhesive. So insulation beads were combined with an adhesive. Now, so that stops insulation from flowing out. But I understand that vibrating that insulation would kind of liquidize it and would enable insulation to be sucked out and then replaced later. So it can be done, but it's not something that I've seen done on a kind of frequent basis.
Okay, Professor, thank you.
Okay.
Any more questions before we conclude?
Yeah, Lobo, you only consider thermal comfort. What about the indoor air quality and ventilation? These are very important issues.
In this particular example, I didn't consider indoor air quality, but thermal comfort, in my view, extends to more like well-being of occupants. So this is what we need to consider in general. And I wasn't going into any specific details of how we achieve thermal comfort. There wasn't really enough time. I have some more material to explain this, especially when it comes to simulations. But thermal comfort, in my view, is a holistic, more holistic than just thermal. It includes complete well-being of occupants, and there's no point designing a zero-carbon building if occupants' well-being is not going to be sustained.
Thank you.
Thank you very much. Any more questions before we close the session? Okay, I don't think there's any more questions. Yes, thank you very much, Professor Lobo. Thank you very much. Very interesting talk and a fantastic way to kickstart our technical talks and technical sessions for the remainder of the year. And I'd also like to thank the attendees for attending. We had a very healthy number today attending. Can I ask the attendees, it'll be to keep an eye out on the ASHRAE UK page. We have quite a few events coming up. One of our biggest events is the CRC chapter regional conferences. Again, it's a meeting that we're having at the University of Oxford, where there's a delegation from all over Europe and abroad, US, joining us as well. So if you're within the area, we highly encourage you to join. I will share the link to this event on the chat, and also we encourage you to be part of the ASHRAE Board of Governors as well. Also, since you joined in for this technical talk, if you have any specific topics you would like us to also present as part of our series, please do get in contact with us, and we'll definitely consider that when we plan our technical sessions for the remainder of the year. Thank you very much for attending. Thank you once more, Professor Lowell, for the talk.
You're welcome.
And hopefully see you guys very soon. Just to let you know, this presentation has been recorded and we'll upload it on the ASHRAE UK YouTube channel. I'll do that as soon as I can, so you can always refer back if there's any parts that you'd like to revisit. And thank you very much for allowing us to record it, Professor Lobo. Thank you very much.
Very welcome.
Thank you all for attending. Thank you very much. Thank you.
Thank you.
Have a good evening, and I won't keep you long before the England game. Thank you.
Thank you. Thank you.
Thank you. Have a nice day.